Alright guys, let's take a look at that activity you did in class the other day. If you haven't had a chance to finish it up, maybe take a few minutes before watching this and finish it up. Otherwise, follow along and see if this all makes sense to you. So this is derivatives of inverses, just generically what happens if you have a function and its inverse. How can you go about finding the derivative of the inverse at a particular value if you know something about the function itself? So let me just pull this in here. This is your sheet. You should maybe pause and get these things down if you don't have them, or just make sure that you do have them. So a couple things to point out. I know as I went around, a bunch of you were talking about the whole one-to-one function thing, simply meaning that for every x there's only one y, and for every y there's only one x. A lot of you said, it passes the vertical and the horizontal line test, and that is also true. So a function is said to be one-to-one if it passes the vertical and horizontal line test. Why does it matter? Because that also means that the inverse of the function will also be a function, which is pretty cool. Moving down, you were asked just about some reflexive points. So you're given the point 1, 8, meaning f of 1 is equal to 8. You can see that on the function over here. And then evaluating the derivative. Well, the derivative of a linear function is just the slope of that function, so f prime of x is equal to 2. Evaluating at the point doesn't change it. It's still going to be 2. It's going to be constant. So for this particular function, you could find the inverse doing the old flip-flop. So you took and substituted an x in for y and a y in for x and went ahead and solved for y. You get that y is equal to 1/2 x minus 1, which is also f inverse of x. So as we refer to the derivative of f inverse, it's going to be important that we recognize that that is what we just found. It is a one-to-one function because f, as we said before, was one-to-one. If we want to find the derivative of the inverse of x, we're talking about the slope of the tangent line. So once again, just for our linear function, the slope was 1/2. So therefore, f inverse prime of x is going to be 1/2 regardless of the value we use. The corresponding point on the inverse graph. So if f inverse corresponds to the point 1, 8, then we know that f inverse of 8 is equal to 1. We can flip the inputs and the outputs of the original function and talk about the inverse function. Give a little scroll tool here. And then if you go and evaluate the inverse at the given value, again, this is kind of silly because the inverse has a slope of 1/2. So regardless of where we take the derivative of the inverse, it's also going to have a slope of 1/2. However, I hope one thing that you did notice was the relationship between the inputs and the outputs of the original function and this function. When we go back up to the top, remember we were talking about f of 1 equaling 8, and we were finding f prime of 1. Again, when we flip our inputs and outputs, when we come back to the bottom to the inverse, the question was about f inverse prime of 8, which was the output of 1. So now we're putting the 8 in as the input into the inverse and getting the slope as 1/2. And hopefully you recognize that these two values, 2 and 1/2, are multiplicative inverses or reciprocals of each other. Sorry, I don't know what happened when I scanned this in. For some reason, half of this is blurry. But the top of the page is leading you through the same process that you went through before. So taking x squared on the domain, x greater than or equal to 0, and looking at the derivative, which should be easy enough to calculate. Oops, sorry, meant to have a pointer tool there. Derivative was 2x. Finding the inverse, once again, can be done. And again, on the restricted domain, we're only looking at the positive value. So the square root of x, which is 1-to-1. We want to go ahead and find f inverse prime down here. So f inverse prime is simply the derivative evaluated at x, so 1/2 radical x. And then you had a little set of values to fill out in your table. I think most of them are readable for you. The f of 3, yeah, I think you can see all of those. F inverse of 9, yada, yada, yada. And again, all of this was leading to trying to get you to see some type of relationship between the input and outputs for f of x and the inverse function. So evaluate f inverse prime of x at the points of f inverse of x, write them down. And some of the things that you should have been seeing is, once again, when you have the input of 9, you're getting a slope of 1/6 when you have the input of 1/25 for f inverse, you are getting 5/2. If you go back up to the table and look at the corresponding inputs to the original function, you're going to recognize that your slopes of 6 and 1/6 match up for f prime and f inverse prime, 2/5 and 5/2, which once again are reciprocals. Shocking. Alright, so for example number 3, another function that you can find the inverse of. So we're looking at the cube root of x, going through the process of looking at the derivative as well as finding the inverse. The derivative is 1/3 cube roots of x squared, and the inverse is just x cubed. Once again, a one-to-one function as shown by the graph. It is going to pass the vertical and horizontal line test, so therefore the inverse is itself a function as well. Again, f inverse prime of x is now just going to be 3x squared, the derivative of x cubed. And in the table, you should have gotten the values that you see here. Once again, if we let me see if I can point out a couple of relationships here for you. F prime of 8. F prime of 8, the derivative evaluated at 8 of the original function is 1/12. All right? Now, we know that f of 8 is equal to 2. So when we go ahead and start looking at the derivative of the inverse function, the derivative of the inverse function is going to yield a 12 when we look at f inverse of 2 taken at the derivative of f inverse. So down here you'll see that when we flip-flop these inputs, so instead of using 8 as the input for f prime, we are using 2 as the input for f inverse prime, we get the reciprocal slope. The same can be shown here again for the negative 1/27th. Evaluating f prime at negative 1/27th, we get 3. Again, the relationship between the negative 1/27th is that f of negative 1/27th produces a y value of negative 1/3. So when evaluating the inverse function at negative 1/3 and taking the derivative, we get the reciprocal slope of 1/3, which goes with that 3. So again, kind of matching up the inputs with the outputs and evaluating the inverse's derivative at the original output of f to generate the reciprocal slope of f prime. Hope that came out right. Alright, for the next page, for number 4, the functions are starting to get a little bit more complex. So x cubed plus 3x minus 5. It is a polynomial function, and since the polynomial function is actually a sum of two one-to-one functions, a cubic and a linear, it itself will be a one-to-one function. It being a one-to-one function is going to yield a inverse that is also a function as well. So we're good there. For part B, guess and check, Wolfram alpha, however you went about doing it. I'm not going to really expect that you went through the synthetic division, but you possibly could have. However, the value of 2 does generate an output value of 9, so we do know that f of 2 is equal to 9, right there, which means that the point 9, 2 is on the inverse, so f inverse of 9 is 2. Flipping the domains and ranges of the two functions again. If we want to find f inverse prime of 9 without finding the inverse function, so finding the inverse function for this would be very difficult due to the multiple x's in f of x. So even by trying to do a substitution and solving for y would be extremely difficult, if not impossible to do. So we need to kind of use all of the patterns that we saw and hopefully get a relationship that will allow us to find the derivative of the inverse at 9. So again, we know that 9 and 2 are going to be related. We know that f prime of x is equal to 3x squared plus 3. So if we take the derivative and evaluate it at 2, we get 15. Again, the 2 and the 9 go together. They are the inputs and the outputs. So if we now look at f inverse prime of 9, not of 2, but of 9, we know that it should be the reciprocal of what we got for f prime of 2. We see that these are multiplicative inverses of each other, or reciprocals. Down at the bottom, can you write a rule? Many of you had this the other day as I went walking around. Some of you, this is where you basically left off. So let's make sure that you definitely have this. So I think we've seen pretty simply if AB is a point on y equals f of x, then BA has to be a point on f inverse of x. What we've been trying to do is come up with some type of generalized formula, and here it is. See if I can get this to work. Whoa, where are you going? I don't know what that just did. Let me come back over here. Yeah, this is what we're looking at. That f inverse prime of the b value, which is the input for the f inverse, the output for f, is going to be the reciprocal of the slope evaluated at the input of a for f. So 1 over f prime of a is f inverse prime of b. I know some people asked about this particular notation. It gets a little crazy when you try to put the f inverse prime together. It sometimes looks a little weird. It looks like you're taking a derivative of -1 or something like that. So sometimes you'll see it written like that as well. And just a little, relationship here that dy dx, the derivative of y with respect to x, is 1 over dx dy. Remember that slopes and dy dx's are just changes in x's and changes in y's. So this whole reciprocal relationship still holds. You can separate that dx and dy and treat it as if it were a fraction as well. All right, and then finally moving on to the last page, number 5. So taking a trig function, which we already know about, but kind of showing that in fact this stuff still works, even though we know a different way of doing this. So given that f of x is equal to sine x, is it a one-to-one function? No, it is not. Clearly the periodic functions have issues with the horizontal line test, so this will not be a one-to-one function, meaning that unless we restrict the domain of its inverse, it will also not be a function. And you guys remember that. That is why we go about putting this whole domain restriction on the inverse trig functions. Again, kind of going through the process here, all of this stuff, hopefully you didn't have difficulty with this. Sometimes it's just a little difficult trying to make sure that you keep your inputs and outputs in the correct spot. But in fact, you can show in part D, and I do want to kind of slow down and go through this a little bit. So let me just kind of zoom in on this one. Taking and looking at the derivative of f of x. So here's f of x is sine x. We know that the inverse is a very specific inverse in this case. It is inverse sine. And we know from our rules that the derivative of inverse sine is 1 over the square root of 1 minus x squared. So we already know that. That was easy to figure out. Now, can we actually show that in fact the derivative of the inverse does produce that? If we look at the outputs and the inputs again, so if we evaluate f inverse prime at sine x, well, we're going to drop in wherever we see an x squared. We're going to put our sine squared down there. We're going to use our little Pythagorean identity that 1 minus sine squared is cosine squared, and the square root of cosine squared is just 1 over cosine x. So we already knew this, that f prime of x is equal to cosine x. It does show us, though, that when evaluating the inverse and taking the derivative at the input of sine x, we do get the reciprocal of cosine x, or 1 over cosine x. So it even works for crazy messed up inverse trig functions as well. All right, so I mean that's kind of where you need to be. Just this this rule that f inverse prime of b is equal to 1 over f prime of a allows you to not have to find the inverse of the function, just be able to evaluate the derivative of f at a and take the reciprocal of it. That will give you f inverse prime for b. All right, we will talk more in class. Make sure you finish up that worksheet. I'll have your quizzes for you next time we meet. Bye.